So, let us think about the boundary layer problem and try to extend that to the jet here. So, boundary layer problem is a Cartesian coordinate problem. Here we are trying to put it in the Rx coordinates, that is the axisymmetric coordinates. Okay, now non-reacting jet. Okay, that is enough for us for the diffusion flames basically. So, let us consider non-reacting jet. Assumptions have to be made. Uniform density, the density will not change. So, constant density, then ordinary diffusion only occurs and obeys Fick's law, and nu equal to d. The usual assumptions what we made. So, nu equal to d. So, the momentum diffusion is same as the mass diffusion. Then important assumption here is the diffusion is predominant in the radial direction only. In the axial direction, there is a jet velocity which is coming out. So, in the axial direction, predominantly convection will take care of the transport. But in the radial direction, that is what the axial velocity component Vx is stronger. So, this will take care of the transport of the fluid in the axial direction convectively. But in the radial direction, it should occur by only the diffusion. So, diffusion is predominant in the radial direction. So, the axial direction, since velocity is predominant, the axial direction diffusion is considered as negligible. So, that is fine. Okay. So, this means I cannot see in the initial potential cohesion etc., where the velocity has not even decayed properly. So, that in that position basically we cannot ensure the diffusion in the radial direction. So, this solution will not start until a given distance from the nozzle exit. The potential there is no the diffusion effect in the radial direction coming in so promptly there. So, we cannot take that. So, this solution will be valid only from a given distance from the port or the nozzle exit, that we have to understand, that is fine. So, we are interested, the jet actually spreads to a long distance, and we are basically we are looking for the location at which the fuel goes to 0 in the axial direction, that will give the flame height for us. So, let us discuss it later. So, in the analysis of jet, these are the simplifying conditions which we have: constant and uniform density, ordinary binary diffusion, that is fuel and air, that is all. There are two fluids, binary fluids which are present. Fick's law is obeyed for the ordinary diffusion. Then Schmidt number is 1. Then diffusion is predominant in the radial direction only, because convection is going to take care in the axial direction. Okay. In the cylindrical polar coordinates, which in 2 dimension axisymmetric coordinates, boundary layer type of assumption is made. What is boundary layer type of assumption? Vx will be much greater than Vr. The radial velocity component is very small. Similarly, the gradient in the x direction is actually smaller than that in the r direction. So, these are the two assumptions invoked for the boundary layer type of problem. So, same type of assumptions are made here. So, we write the conservation equations, continuity equation, dou Vx by dou x plus 1 by r dou by dou r times Vr. So, that will be equal to 0. So, simple equation is this continuity equation, mass conservation, steady state problem. Okay. So, there is no time dependent terms involved in this. Similarly, axial momentum equation, Vx into dou Vx by dou x convective term plus dr dou by dou r of Vx. So, the axial momentum conservation. So, Vx is put in the convective term here, and here you can see the pressure gradient also is negligible, pressure gradient. So, here you can see this is diffusion term, and as we have assumed only the radial direction diffusion is taken into account here. So, the rho from the left hand side has come to the right hand side, and you get this value is nothing but nu, the momentum diffusivity. So, 1 by r dou by dou r times dou Vx by dou r, that is the diffusion term only in radial direction. Okay. So, this is the conservation axial momentum. Please understand that since Vr is much less than Vx, we assume that is a boundary layer assumption, like along the x direction the velocity, that is predominant than the y direction velocity. So, we neglect that. Similarly, here the radial direction velocity is neglected. So, there is no momentum required for the this velocity. So, what we do is we will try to solve Vx using this axial momentum conservation and solve Vr using the continuity equation. Apply that Vx value here and get the value of Vr. So, two equations, two unknowns are there for the velocity components. So, that is enough. So, pressure is not there. So, two equations, two unknowns, you can solve this. So, there is no separate equation required for the radial velocity. Okay, next fuel conservation, that is again convertive term Vx into dou yf by dou x plus Vr dou yf by dou r, convective term equal to diffusion. So, diffusion is d 1 by r dou by dou r into dou yf by dou r. So, this is the conservation of the fuel species. So, once you get the conservation of fuel species, oxidizer that is air, here nitrogen plus oxygen together, the mass fraction of that can be found by 1 minus yf. So, that is what we are going to use. Okay, now please see that the we have already assumed that dou by dou x is much less than dou by dou r, but why you are retaining this term? Because Vx is very strong. So, since Vx is much greater than Vr, since due to Vx this term stays, not due to dou by dou x of yf this stays, this term stays because of Vx. Similarly, here dou Vx by dou x may not be very high, but Vx is very high. So, by scaling this term stays. Okay, so but here you can see that this term, due to the radial gradient of Vx, this term stays. Vr may be very small, but the gradient of Vx in the radial direction is dou by dou r of Vx is very high. So, due to that this stays. So, this we can't cancel anything, but in the diffusion term dou by dou x is cancelled, because dou by dou x second derivative of that is not very high for the Vx. So, that has been neglected. So, that we have to understand. So, the terms are chopped off when they are not required because of the scaling analysis, which are due to these two equations what is written here. So, these equations are boundary layer type equations. Diffusion term in x direction and momentum equation in the radial direction are absent due to scaling analysis. Vr is much less than Vx, dou by dou x is much lesser than dou by dou r. Okay, so these are the three equations which we need to solve, but please understand again partial differential equations, non-linear because of the convective terms, and we have to solve this. But anyway, as Blasius did the solution for the boundary layer equations in the Cartesian coordinates, this again using the self-similar profiles, we can try to get the solution for this. So, that is what we are going to do next. Okay, so before that we are going to the solution, we need to see the boundary conditions. So, we have three equations now. The mass conservation, which is going to pretty much give us the value of Vr, and you can see this is dou Vx by dou x plus 1 by r dou by dou r times Vr equal to 0. Then we have the axial momentum equation, convective term Vx into dou Vx by dou x plus Vr times dou Vx by dou r equal to, in the diffusion term there is only radial direction diffusion and pressure gradient is also absent. This equation, if we solve these two equations, momentum and the axial momentum and the mass, you can together solve to get the velocity components Vx and Vr. Then the fuel conservation is going to be solved to get the value of Yf. And here also you can see that only the diffusion of fuel in the radial is considered. Actually, convective term is going to take care of that. So, this is the thing. Boundary conditions for this. So, we have to specify boundary conditions at three locations: r equal to 0, r tending to infinity, then x equal to 0. Okay, parabolic equations. So, these are the boundary conditions we have to apply for this. So, what are the boundary conditions? So, they are at axial the center line axis r equal to 0, Vr is 0, okay, there is no Vr is exactly 0 there. Gradient of Vx in the radial direction will be 0 at the axis. So, dou Vx by dou r at this radius equal to 0 at any x location along the axis should be equal to 0. Vx cannot be 0, Vx is decaying, but it will not be 0, but the gradient of that will be 0. Then similarly, gradient of Yf, radial gradient of Yf at the axis at any x will be equal to 0. So, these are the conditions at the axis, this axis at the axis, that is r equal to 0, we have the radial velocity is 0 there. Otherwise, radial velocity will be there at other for or locations. Radial velocity need not be 0, but at the axis, due to symmetry, this should be there, and again due to symmetry, the gradients of the other variables should be equal to 0 in the radial direction at r equal to 0. So, this is one of the boundary condition at fixed at the r equal to 0. Then we see far off radius or tending to r infinity, or as I told you, it may not be exactly infinity, you cannot use infinity. If you numerically want to solve this, we have to go for say 100 times the radius or something like that. So, long far field you take. So, where you can see that the asymptotically the value of so this is actually Vx, asymptotically the value of the velocity and the Yf tends to 0, correct. Even Vr will be 0, so you can also say Vr. So, Vr also will tend to 0. All the velocity component is still air present. So, okay, once the jet is there, far from the jet there will be no movement. Okay, so that is what the jet is actually getting into a very still air environment, quiescent environment. So, far from the jet axis, the values of the velocity should be 0. Similarly, there will be no fuel present, only air will be present. So, velocity components plus the fuel mass fraction will tend to 0 at far locations. This is the second boundary condition at the r tending to infinity or higher, very high r value. Then at the exit of the nozzle or the port, okay, there are boundary conditions which actually defines when the radial direction distance is less than or equal to the radius of the port, that is small r less than or equal to capital R, where we know that the average velocity can give here. Vx is the average velocity is getting out of the port. Similarly, Yf will be Yf at exit. It may not be 1, but in this case only fuel is coming out, so I am assuming it as 1, that is fine. Similarly, when at x equal to 0, when r is greater than the radius of the port capital R, then these quantities are 0. So, these are the boundary conditions. Do you understand? So, parabolic equations, the boundary equations are parabolic in nature. We need boundary conditions to be specified at these locations r equal to 0, r tending to infinity and x equal to 0. And for all the variables what we are considering, we are trying to solve it. Okay. So, now this you can numerically solve. If you apply this boundary condition and solve this, you can numerically solve this. But theoretically, we can do it by doing what exactly Blasius did. So, Blasius transformed this partial derivatives to ordinary Gaussian equation, third order ordinary Gaussian equation, differential equation, and he solved using a similarity variable. Similar to that, when you normalize Vx at any r and x by Vx at r equal to 0, the central line value, which is the maximum, and then its radial distribution becomes universal depending only upon a similarity variable r by x. So, if you define a similarity variable r by x, then we can solve the problem exactly like what Blasius used for boundary layer approach. I am not going to the derivations of the solution, but I will only present the solution here. So, you can see that these parabolic equations, boundary layer type of equations result continuity, then axial momentum, then fuel conservation equations. Then you can solve this numerically by these boundary, applying these boundary conditions at r equal to 0, r tending to infinity and x equal to 0. Or we can use a theoretical analysis what Blasius used, similarity approach, and get the solution. Now, the similarity solution is presented here. As I told you, a similarity variable is required, which is r by x, a function of r by x. So, that variable is defined like this. Okay. So, that is this say as I told you, similarity variable is r by x. So, psi is the similarity variable. Psi is defined as some constants. These are constants. So, rho e density is assumed as a constant, and at the exit it is a constant. Momentum, initial momentum of the jet Je, that is also a constant, 16 phi. So, this is a constant times again mu actually can be a constant here, because again the assumption mu can be a constant. So, r by x. So, this is actually defined as some constant times r by x. So, similarity variable is defined. So, once you use the similarity variable and also normalize the axial velocity with the central value, normalize this, then you get the solution in terms of this. So, this is solution for Vx, that is the actual velocity at any x location. At any x location, Vx at any x location will be 3 by 8 pi Je by mu x 1 plus psi square by 4 the whole of minus 2, this whole power minus 2. Similarly, R profile, you can see that R profile is also given like this. So, as I told you, these are going to be applicable only after a particular distance from this, away from the potential core, okay, jet exit potential core, away from that only the similarity will be there. So, if you see the profiles again, the profiles are going to be self similar only after a particular axial location. So, which is actually much greater than xc, the potential core. After a distance from the potential core, when you apply that Vx by Vx naught versus R by R off, then you collapse this. So, below that you cannot do that, as you can see here, you cannot collapse here at x equal to 0 and x equal to x1, you cannot collapse by using that rule. So, only away from the jet exit or the nozzle exit, this solution will be valid. So, whatever solution I am posing here, these are valid only at a region far from the port exit, that you have to understand. So, that is enough for us basically. So, we don't need to concentrate our solution the near field, only the far field we will try to apply. So, this is the equation. Similarly, you can see Yf. Yf is nothing but Vx by Ve. So, the same profile we got, correct. So, Yf is nothing but Vx by Ve, and that varies exactly like this, you can see this. So, now instead of this I am trying to put mu, instead of mu I am putting mu by rho equal to nu equal to d. So, this is the thing. So, d I will say. So, this is the Schmidt number equal to 1. So, when I apply the Schmidt number equal to 1, so mu I take rho e from the Je. So, Je you know, so Je is nothing but rho e Ve square pi r square. So, when I substitute here pi r square Ve square, that Ve here you can see that Ve stays here, then mu by this rho e comes to the bottom. So, mu e by rho e will be d, which is mu equal to d. So, that is what I am getting here. So, one of the Ve, the Ve square, one of the Ve cancels out because Vx by Va I am putting. So, that cancels, this Ve cancels one of the V in the product here, V square. So, V alone stays, pi r square stays, Ve stays, mu, that rho comes to the bottom. So, mu by rho equal to nu. So, nu equal to d. So, I am substituting d here. So, this is the variation of Yf. Okay. See, because this is R and X are there, it is applicable to any radial location. I can vary the R here and similarity variable will vary, so that I can get the profiles. Okay. So, this is the solution I get. Okay. So, similarity solution is the one which will make a, see, for example, all the variables like Vx and Yf are function of both R and X. But if I define a similarity variable which is a psi, which is a function of R by X, seeing the self similarity in the profiles away from the nozzle exit, then I can have only one independent variable psi, and I can express my solution as a function of that particular variable psi only. So, that is what I am trying to do here. So, at any x you can do this, and this is the profile. So, now if you want to plot here, so non-dimensional velocity, non-dimensional axial velocity and mass fraction distributions are given here. Basically, this is the Vx by Ve, so which is equal to Yf, that is the profile here. So, that is what I get 0.375 rho e Ve r by nu. I am jet momentum I am expanding now, and getting this value, you may remember this is rho e, rho into velocity into characteristic dimension, which is the radius, divided by mu, which is the Reynolds number of the jet. So, it is jet radius, jet exit velocity, jet density divided by mu I am using. So, this is the jet Reynolds number. Okay. So, now this Vx by Ve, okay, can be defined as 0.375 Reynolds number of the jet, x by r power minus 1, 1 plus psi square by 4 whole power minus 2. So, this is the distribution for both yx and non-dimensional axial velocity. So, now if you want to get central line profile psi is set to 0, that is all, psi, because r by x, r equal to 0. So, r by x is set to 0, then you will get the central line profile. So, for central line profiles, set psi as 0 in this equation, you will get the central line profile, the decay, velocity decay, etc. So, for example, if you set psi equal to 0 here, then this terms goes, then you get only Vx central line. So, Vx comma 0 will be without this term. Okay. So, that you will get central line profiles you will get. So, that you can use. Similarly, central line decay of the yf also you can get. Now, for half width and the splitting angle, we use this r half by x equal to 2.97 by, I have not given the derivation, this is the, you can try to derive it or see some books to derive this. So, r half by x equal to 2.97 divided by the Reynolds number. Okay. So, when Reynolds number increases, then the r half will decrease. Okay. So, similarly, this jet splitting angle alpha is tan inverse of this r half by x. So, you can use this. Okay. Now, as I told you, far field only the solution is valid. That means x by r should be greater than 0.375 into Rej for the solution to be valid, this solution to be valid. Okay. Now, what is flame height? Now, the diffusion flames basically are transport control. We have already seen that it is transport control, that chemical kinetics does not play a role, because chemical kinetics are very fast when compared to the time of this diffusion. The radial diffusion time, molecular diffusion is actually much slower and the chemical reaction is much faster. So, when a fuel molecule travels from the central line to the jet edge, where you can also see the oxygen diffusing in the radial direction towards the central line. At some point in the radius, the fuel molecule and the oxygen molecule will mix at some stoichiometric proportions, where a flame zone will be formed upon ignition. That flame zone will be very thin. When you plot the locus of all this, you will see the flame surface basically. So, this is transport control. When you have more momentum for the jet, then you can see that as I told you, when Reynolds number increases, then r half decreases. That means your radius of the flame will decrease and so on. So, exactly where the this will come, the flame surface will come, that is actually you have to calculate the stoichiometric value of the fuel mass fraction. So, that is nothing but 1 divided by 1 plus air by fuel stoichiometric air fuel ratio, 1 plus stoichiometric air fuel ratio of inverse of that will give you the stoichiometric value of yf. So, if you trace that, basically you will get the flame profile. So, laminar jet diffusion flames. Yeah. So, fuel jet which is coming out with some momentum, which will entrain the air due to the viscous effects which we saw. After the potential core region, you can see that the viscous effect will be more and the mixing takes place, indicated by the reduction in the velocity value and the value of the mass fraction of the fuel. Okay. So, air entrains from the atmosphere and the jet spreads along the radial direction. As I say, the radial direction, you can see the more the yf value of the central line decays at a larger radial distance as you go along the axial direction. Okay. Now, oxygen from the ambient air and the fuel mix, and when ignited, a flame zone is formed at locations where the mixture composition is around the stoichiometric value. Okay. So, fuel from the central line decreases like this, oxygen from the ambient diffuses like this. Okay. So, somewhere it will form a stoichiometric mixture. So, this if we ignite here at this location where they are mixed at a stoichiometric, this is fuel and this is the oxygen. So, they somewhere in the radial direction, this is the radial direction basically, or some radial location they will form a stoichiometric mixture. So, yf stoichiometric, what I told. So, that value is attained. So, when you ignite in this location, flame will form. The diffusion of fuel and diffusion of oxygen in the radial direction are much slower when compared to the chemical kinetics, or we can say the chemical kinetics is much faster. Okay. So, at this location the flame is formed. Okay. So, that is what is given here. The oxygen in the ambient and the fuel mix, and when ignited a flame zone is formed at locations where the mixture composition is around the stoichiometric value. Okay. Now, so this is the stoichiometric value. Okay. So, there the flame will be formed. So, this is at a particular x location. So, if you trace all the x locations, you will get the flame surface. So, these type of flames are characterized by the visible length. Okay. So, for example, I will show you the figures later. So, visible length, jet of the fuel comes out and you ignite this, a flame forms. So, what is the characteristic of this flame? Is the length. So, okay, for a given fuel flow rate, okay, you will get a particular length of this laminar flame. So, that length is the characteristics. So, when you saw the premixed flames, the laminar flame speed was the characteristic, one of the characteristics of that, correct. Based upon, for example, in the Bunsen method, Bunsen burner, you get a conical flame, and a cone, half cone angle is used to calculate the laminar flame speed. So, that is the characteristic of a premixed flame. But in the case of a diffusion flame, okay, like this, where nothing is mixed and they mix only at the flame zone like this. So, under that circumstances, the distance what the fuel travels to get all the oxidizer it needs, that is the characteristics. So, we will say visible length of the flame which is measured by the burner exit will be the characteristic important feature of the diffusion flame, and that indicates the distance the fuel has to travel to get the required amount of oxidizer for its complete oxidation. So, that is the important thing. So, flame length, okay, flame length, which is what we are going to see for as a main characteristic of a diffusion flame or a non-premixed flame. Okay. Now, again I am repeating here, the fuel molecules travel, okay, through molecular diffusion in the radial direction and by convection in the axial direction. Because you can see the convection is predominantly in the axial direction because of the jet momentum which is coming from the nozzle exit, but in the radial direction it is only by diffusion, concentration gradient driven. So, of course, solar effects also will be there, but predominantly it is diffusion driven.